Barrett. I'm a research associate within the software development team at King's College London. I work with these fine people you see on the front slide here. And this is collaborative work with all of those people, to be clear. This talk is going to be all about why possibly VM benchmarking could be misleading you. So who benchmarks VMs or runs benchmarks in general that involves a VM? Hands up. Excellent. This talk is for you. Enjoy. So this talk is all about the outcome of this research paper which was published in UPSLA last year. The title is Virtual Machine Warm-Up Blows Hot and Cold. It's a research paper which is all about it's about the way that we measure benchmarks on VMs. And more specifically, it focuses on what we call the warm-up of our VMs. Okay, so what I'm going to do in this talk is I'm going to first go over some benchmarking concepts, and then I'm going to describe an experiment that we designed and executed, and then I'll show you some results. So let's begin. So we start with some benchmarking concepts. It's probably no surprise to you that if you want to benchmark a VM that contains a just-in-time compiler, you will have to invoke that VM. So that VM has a lifetime. The lifetime is from the beginning of when you invoke it up until when it exits. And for the purpose of this talk, we are going to call that a process execution. Now, once you've got your VM up, what you're then probably going to do is you're going to run a benchmark in a loop, and you're going to be timing the iterations of that benchmark. And for the purpose of this talk, again, we're going to introduce some terminology. We're going to call that these in-process iterations. And I'm going to use this terminology throughout the talk because otherwise it gets quite confusing. So with that terminology in mind, for each process execution, you can generate a run sequence plot like this. So it's a pair of axes. On the x-axis, you have the in-process iteration number, and that is ordered. And then on the y-axis, you have the corresponding iteration times. Obviously, lower is better on the y-axis. It means that your VM is running faster. Now, because I'm talking about VMs that contain just-in-time compilers, we don't expect to see uniform performance across the entire process execution, because just-in-time compilers do things like adaptive compilation, dynamic compilation techniques, etc. So we might actually expect to see something like this. What you can see here is that the VM goes through several phases, if you like, throughout its lifetime. And the different phases have different performances. So let's talk about what these different phases are. In the beginning, the VM is typically in what's called the profiling interpreter mode. It's interpreting the user's program, but at the same time, it's trying to figure out which pieces of code are frequently executed, which types arise, maybe which values arise. It's trying to get a picture of how the user is using this program. And at some point, the VM will decide it has enough profiling information to enter the next stage, which is called the compilation stage. Here, we take everything we've learned from our profiling, we chuck it into a code generator, and we dump out executable code. The idea is that this executable code will be much faster than what we had before. And that brings us to the holy grail of the steady state of peak performance. I'm sure you've all heard this terminology. And this is typically what everyone wants to measure when they're benchmarking their VMs. Now, you're looking at that plot now, and you're a bit skeptical, perhaps, because it's got too many straight lines, right? So really, we actually expect something a bit more like this. You can see immediate difference, I hope. So first of all, there is some noise here. Why do we see noise? The reason we see noise is because there are lots of non-deterministic things happening in a computer and the surrounding environment. So for example, the operating system is non-deterministic, the VM is non-deterministic, the hardware is non-deterministic, even the room that the computer is sat in is actually non-deterministic. So for example, the temperature could be fluctuating. So that's why we see noise. The second thing you'll notice is that there are two steps down onto the steady state of peak performance here. What I'm trying to show there is that compilation doesn't necessarily have to happen all at once. There could be several phases of compilation before we hit peak performance. And then finally, you'll notice this spike. You may see spikes if you have, for example, a VM which has a stop-the-world garbage collector, and it has to stop the user's program temporarily while it sweeps the heap and cleans up anything that's not used. So we do expect to see spikes. So this talk is about this phase here. This is the warm-up phase. It's the interval after the VM starts up until we reach peak performance. So why would this be an important thing to talk about? Well, there are two kinds of people who do not like bad warm-up. The first is users, although they may not know it. The reason users don't like bad warm-up is, to them, this could be a program which is taking a long time to get up to speed. Perhaps the user interface is laggy. They perceive it as just being slow. They'll just say it's slow, basically. So that's why users dislike bad warm-up. However, VM authors also really dislike bad warm-up. So this is for a different reason. VM authors typically want to be saying, look how fast my VM is, it's faster than yours, right? The warm-up phase is the slowest phase for their VM. So they don't want to present that result. They'll typically try and discard it if they can. So you'll see in benchmark harnesses where they say, let's run the benchmark 10 times and throw away those measurements before we actually start measuring. It's because they want to have the best shot at saying their VM is faster than yours. So in summary, warm-up is important. It's something that we should be measuring. However, in the literature, there is not a great deal of information or any experimental results of any kind that actually measures how long warm-up typically takes. So this is really where we enter the arena, if you like. We decided that we would design an experiment which does exactly this. So we're going to design a benchmarking experiment which doesn't just focus on peak performance, it focuses on how long warm-up takes. And we do this for a ton of different VMs that are floating around in our ecosphere now. So our working hypothesis was that if we take small and deterministic programs, then they should reach a steady state of peak performance. Seems like a reasonable hypothesis, right? So bear that in mind, we'll come back to this hypothesis. What I'm going to do now is I'm going to take you through the design of our experiment so you know exactly what we're doing. And then once we get past that, I'll show you some plots, and then we'll talk about some numbers. So let's do that. The first thing we have to talk about is which benchmarks should we actually think about running. And there are lots of different benchmarking suites. We wanted one which was cross-language, of course, because we're going to measure lots of different VMs that target different languages. Now, maybe controversially, we chose the computer language benchmark games. This is usually considered a pretty bad benchmarking suite. It's usually criticized for being a little bit unrealistic. The programs are perhaps a little bit too small. But bear in mind that our hypothesis speaks about small and deterministic programs. So unusually for us, this is absolutely perfect. And of course, we didn't just take them off the shelf and run them. We did a bit of auditing to check that they are sane. So for example, we removed any what we're calling control flow graph non-determinism from our benchmarks. What this means is that when I repeat a benchmark in the same process execution, the exact same control flow paths should be taken. We do this because we want to give the VM the best shot at stabilizing if we can. And there were a few bugs, actually. There were a few cases where random number generators weren't being reseeded, for example. So we had to fix those. We also added checksums to all of the benchmarks that didn't already have them. Now, a checksum is just really a fancy word for a number which is being computed as part of the benchmark's workload. The checksum is very useful for us for two reasons. Firstly, it ensures that what we can do is we can generate an expected checksum value. And then what we can then do is compare each in-process iteration, its checksums against the expected checksum. This tells us that all of the in-process iterations are doing roughly the same work. Because if a different checksum value came up, then this would mean that perhaps some different amount of work had been done. And of course, we can then also take those expected checksum values and share them across all of the different language implementations. So that gives us an idea that all of the different language implementations of the benchmarks are doing roughly the same work too. So that's which benchmarks to run. Now, how long should we run our benchmarks? Depending on who you ask, you'll get different answers. Some people might say, oh, I just run 10 times. Some people say, I run 30 times because that's the bare minimum to, I need to generate a confidence interval. I've heard that before. Some people might say, I run 50 because I don't want to run the bare minimum. So we actually decided to run for way longer than most people would consider necessary. We ran 2,000 in-process iterations and then repeated this 30 times with fresh process executions. So the plots that I mentioned earlier, there will be 2,000 long on their x-axis, and there will be 30 such plots for each benchmark and VM combination on each machine that we benchmark on. That was a mouthful. So that's how long to run. These are the VMs that we used. So there are a handful of different VMs targeting different languages. These are all the current versions at the time of the experiment. So these particular versions were current as of the beginning of this year. Now, the elephant in the room here is GCC. GCC is not a VM. GCC certainly doesn't contain a just-in-time compiler. So the reason GCC is in the experiment is, firstly, it acts as a baseline, and secondly, we use this version of GCC to build all of the above VMs, thus eliminating versions of GCC as a source of variation in our benchmarking experiment. Next, which machines did we use? We used 3 different machines. 2 of them run Linux, 1 runs OpenBSD. The 2 Linux machines have an identical operating system with an identical packing list with identical configurations. However, the 2 Linux machines do have different hardware. One has a server chip. The OpenBSD machine is more similar to the first Linux machine, although it has a different amount of RAM. And of course, we have to do all of the things that conventional benchmarking wisdom tell us, like turning off turbo boost and hyperthreading, because clearly these will inject variation into the benchmarks, and we want to give the VMs the best chance possible at stabilizing. So next, how should we actually run and collect data from our benchmarks? Now, most people just run a very small benchmarking loop and write samples to a file in a very simple fashion. We wanted to do something which was a bit more intricate. We actually used our own benchmark runner, which we call CRUN. And the idea behind CRUN is that it controls as many confounding variables as is humanly and practically possible. What we wanted to do was constrain all of the environment around the benchmark, but not the VM or the benchmark itself. So we want to exercise all of the VM's behaviors, if possible, whilst constraining the environment. So I don't want to measure variation in the kernel. That's not interesting. I want to measure just the VM running the benchmark, its full set of behaviors. That's what we're all about. And to do that, CRUN checks or sets the environment in such a way that it tries to constrain the environment. So we minimize I/O, we set memory limits, we drop privileges to a fresh user account for every process execution, and that includes destroying the home directory and recreating it. It reboots the system before every process execution, so there's no sort of state hanging around in the hardware or the kernel. It checks the demessage buffer for changes. It checks that the system temperature is roughly the same for every process execution, and checks a load of kernel settings, etc., etc. I don't have time to go through all these in detail, but I will be giving a talk at the Benchwork workshop, so if this interests you, then I can talk about this in a bit more depth there. What I'm really trying to get across here is that we went the extra mile in thinking about how to constrain the benchmarking environment to give those VMs the best possible shot at stabilizing. Okay, so finally, once we've got all of this data, we've got this huge corpus of data, and the question now is, what are we going to do with it? In the early stages of this experiment, it became very clear to us that taking a mean and generating confidence intervals is not going to cut it. So we actually got a statistician on board to help us develop an automated and more intricate analysis for our data. And it's based on a statistical method called change point analysis. So change point analysis works like this. We take one process execution's worth of data. So I'm showing you a plot. What we then do is identify outliers and ignore them on the assumption that they're probably GC spikes. Fine. What we then do is we run a change point analysis across our data, which identifies these so-called change points. Change points in the plots you'll see in this talk are the horizontal dashed red lines. And between the change points, you have change point segments. And what a change point segment is it's a collection of consecutive samples which have very similar mean and variance. So in other words, what we're trying to do here is we're teasing apart all the different phases in the results for each process execution in an automated fashion. And then using the pattern of change point segments, we can then say how well the process execution warmed up. So for example, if there's just one change point segment, then we call that flat, because there was no real change in performance apart from perhaps a bit of noise. That's absolutely fine, as we mentioned earlier. Now, if there was no change point after the 1,500th in-process iteration, and the last segment is the fastest segment, then we say the process execution has warmed up. If, however, there was no change point after the 1,500th in-process iteration, but the last segment was the slowest segment, this means we were faster before. So that means that the VM has slowed down. And of course, that shouldn't happen. And the only other case is that the VM didn't stabilize. We say the VM didn't stabilize if there's a change point in the last 500 iterations of the process execution. And the reason behind that is really, we're not really sure whether there could have been another change point, say at iteration 2001 after we stopped measuring. So we can never really say whether it's stabilized, but we say that if it's not changed in 500 iterations, there's a good chance it's probably stabilized. And that was a slight simplification of the algorithm because there is actually a tolerance involved. So if there are two change point segments that are very, very, very close to each other, we consider them the same segment. Okay, that's the design of the experiment out of the way now. So now we can start talking about results. Before I show you any results, just note that we've been running this experiment many times. So the data that you see in the OOPSLA paper is an older version than what I'm showing you now. It doesn't really matter because the story is the same. So first we'll look at some plots, then we'll talk about numbers. Let's look at some plots. So this is a run sequence plot. You know about the axes on this already. The red dot is an outlier. This is nbody running on PyPy on a Linux machine. In the brackets up here, you see the algorithm's classifier. So it's classified this as flat because there is one change point segment. This is absolutely fine. You can generate statistics for this very easily. Wonderful. Some process executions did warm up, which is good because we want to see that. This is faster, running on V8 on a Linux machine. The little inset plot here is just showing a zoomed in part of the data so you can see finer detail. So it's showing the beginning of the process execution here. So this is fine. It warmed up. It took quite a long time to warm up, but it warmed up nonetheless. So about 600 iterations for this to warm up. And here's another example of warm up with a lot of outliers. That's spectral norm running on PyPy on a Linux machine. Okay, this is where it turns bad. Many process executions slowed down. We just didn't expect this. This is Richards running on Hotspot on a Linux machine. So that's a very well-known benchmark on a very mature VM on a very used operating system. What we see is we see an initial speed up. If you look at the inset plot here, you can see there was a speed up. After 2 iterations, we're on a quite a fast state. And then around about iteration 200, we slow down by 5%, and then we're stable. So what's happened here is we've converged on the steady state of the worst performance, I guess. This shouldn't happen. This is the opposite of what a JIT should do. It should always speed us up, not slow us down. I suspect that the reason that this has happened, by the way, is because we're probably the first people to run the benchmark this many times. Just speculation, not sure. And here's another example of slowdown. This is faster running on V8 on a Linux machine. And what we see here is several steps up onto a steady state, which is not as fast as what some of the states we've seen before. Again, shouldn't happen. Many of the process executions did not stabilize. This is binary trees on V8 on a Linux machine. There is a change point around about iteration 1800, so we cannot say that with confidence that this has stabilized, so we say no steady state. And what's even more depressing is that if you repeat these process executions, often you see different behaviors. So you're seeing here the same benchmark on the same VM on the same machine. The plot on the left is warmed up. The plot on the right didn't stabilize. So this says something about the repeatability of process executions. Okay, so you saw the behaviors that we saw. Now let's talk about numbers. Let's quantify this. For each machine, we generated a large table like this, which I don't expect you to be able to read. What we'll do is we'll zoom in on one section of this table. So this is just the part of the table showing the spectral norm benchmark. And the way we read this is on the left we have the VMs, and then the next column over, class dot, that's standing for classifier. Then we have the steady state iteration number, if we reached a steady state, of course. Then the same again, just in seconds. And then this is the one that most people are trying to already measure when they do benchmarking, which is the steady state performance. So let's look at a couple of columns. So C, running spectral norm. Oh, that doesn't look very nice. Okay. Has the classifier symbol. It's like an equal sign with a cross through. This means inconsistent in a bad way. Inconsistent because more than one behavior arose, but in a bad way because, and what we do now is we look inside the brackets, we can see that there were 27 warm-ups, 2 flats, and 1 slowdown. So the existence of that slowdown was enough for this to be classified inconsistent in a bad way. The next one down is showing Graal running a Java program, spectral norm Java program. This has just the one symbol, which is the slowdown symbol, which means that all 30 process executions consistently slowed down. Let's look at, say, PyPy running spectral norm. This has just means inconsistent in a good way. And that's inconsistent in a good way because 27 process executions were flat and 3 were warm up. And we don't really consider flat to be bad. That could have just been a really fast warm up. We don't know. Okay. So as I say, we get one of these large tables for each machine. But what we can do is we can flatten that down into some summary statistics. I'm not going to spend time on this. I'm going to flatten it down even further for you. It's just to give you something that you can take away from the talk. Let's forget about OpenBSD for a minute because OpenBSD can only run a subset of the VMs, so it kind of colors the results a bit. Let's talk about Linux, which is what a lot of you are probably using. So we had 2 machines remaining. So we can say that good warm-up, which is either flat or warm-up, consistently occurs for between 67.2 and 70.3% of process executions, depending upon which of those 2 machines you look at. So there we're just talking about process executions in isolation. That's not a very good metric for us because it doesn't take into account consistency, of course. So what we need to do is we actually need to pair them, put them into pairs. So if we talk about VM and benchmarking pairs, then only 37.8 between 37.8 and 40% of these pairings, depending upon which machine you're on, would warm up in what we call a good way. So that's less than half of the data would be useless, is effectively what we've concluded there, which is shocking, quite frankly, a bit depressing, very interesting. So the hypothesis is kind of out the window at this point. Bit depressing. Never mind, let's move on. So the next thing we ask ourselves is, why on earth does this happen? Because everything I've been taught about benchmarking isn't true, or is it, or have we done something wrong? So 2 things which came to mind which could be affecting our results are bugs in, for example, the JIT and the GC. These are things which can change the performance of the VM. So what we did is we went back and we instrumented PyPy and the JVM so that they could tell us on an in-process iteration basis how much time was spent in the JIT and how much time was spent in the GC. So the bottom plot that you see here is just the normal run sequence plots that you've already seen, but then we have time in the JIT and time in the GC. So if you look at the run sequence plot here, you see that there are lots of different change point segments, kind of a strange pattern really, but you'll also notice that the samples on the change point segments are on a very sort of gradual upward slant. It's kind of hard to see, but it's there. So that suggests to me maybe some kind of resource leak or something along these lines. But anyway, if we look at the time spent in JIT, we just see JIT activity in the beginning of the process execution and then idle for the rest of the process execution. That's good. That's what you'd want to see. What you wouldn't want to see, however, is this very tight coupling between the time spent in the GC and the wall clock time. So this tells me that really all we've measured here is something going on in the GC, which isn't really what we're setting out to do. So that turned out to be a bug in PyPy's garbage collector. And here's another example where that kind of instrumentation can tell us what's gone wrong. So this is the Richards on hotspot example again, where it slows down at iteration 200. If we look at first time in GC, we see regular spikes, which is kind of good. That's, again, what you'd expect. However, the time spent in the JIT, you'll notice that there is JIT activity in the beginning. There's also JIT activity around iteration 200. So there is a JIT event coinciding with that 5% slowdown. So that suggests to me that this is probably a JIT bug. Perhaps the JIT has generated code which is slower than what it had before. So in some cases, we could look at these kinds of plots and say, yes, that's why strange things happen, but the sad truth is in many cases, you just cannot say looking at those kinds of plots. So there are still mysteries to be uncovered here. You know, we haven't completely explained why we see strangeness. Okay, so we're getting to the end of my talk now. What have we learned from this experiment? So I think we can say that benchmarks don't warm up as we expect. We've also learned that if we repeat a benchmark, you often don't see the same warm-up characteristics every time, which may be surprising. An open question now is, have we been misled by our inability to benchmark accurately? Have we implemented optimizations which do nothing? Or have we implemented optimizations which are bad? Because this could be possible, of course. What can we do about this? We don't have any silver bullet, unfortunately. I'm very sorry about that. We do have a few pieces of advice, however. First of all, if you've run your benchmarks for longer, you're more likely to uncover some of the issues that we saw. So all we did there was really run for 2,000 in-process iterations to discover some strange things happening. Maybe consider doing the same. We should all accept that peak performance may not occur. So the practice of just running a benchmark for 10 times and putting a comment on the line saying, warm up the VM, it's not going to cut it anymore. Clearly, it's more complicated than that. So we have to report our numbers in such a way that caters for the fact that the VM just may not have stabilized. We can't always blame GC or the JIT, as we've just learned. I think we should always be reporting our warm-up time as well, because it is actually a metric which impacts users. And finally, should we be engineering our VMs for a bit more predictable performance? And I know that's very easy to say, but it's probably very difficult. But it's something that we're starting to think about within our team. So here are some links to the original paper and the code. All of our code is open source on GitHub. Our data is also available on archive.org. So if you wanted to analyze it independently, feel free, go ahead. Okay, and that brings me to the end of my talk. Thanks for listening. Hope you found it interesting. And we can do some questions now.
Hi, awesome work. I'm glad that you're doing this. Often VM engineers kind of do a hill climbing algorithm when they're optimizing, like making small tweaks to the JIT, and those tweaks are so small that we can't necessarily see the impact of those. Have you thought about this problem and how you might use some of your techniques to get insight there?
We haven't thought about doing hill climbing, but what we do have is, I don't know if this is going to answer your question exactly, we have a way of diffing the large table that I showed you. So we developed this because we envisaged a scenario where you have some kind of continuous integration and you want to know whether a change you've made has made a difference to the warm-up classifications. But it doesn't, it's more simple than hill climbing, for example, that we're not looking for like local minimas and things, it's just, did it change for the better, did it change for the worse, or did it just do something slightly different that you can't say is better or worse? Do you think it could be integrated into this kind of?
I would love to see this on our performance infrastructure. This would be awesome.
Well, we can help you do that.
How much money do you want?
How much you got?
All right, we'll talk later.
Yeah, hi. Fascinating work. So you had this slide where you showed that you went the extra mile to control all the variables. Mm-hmm. Did you get any insight into which of these variables actually mattered in the end?
No, and this is something I want to actually investigate. So I've been thinking about this. It's harder than it seems because, okay, so you could actually measure all of these things in isolation, couldn't you? That would be fairly simple. What about interactions between 2 or 3 variables? Then you have this explosion of combinations. So you'd need some kind of heuristic to kind of narrow the scope of the experiment. And there was a guy at ARM doing something similar to this, which I've been thinking about that a bit as well. But yeah, good question, good question.
Thanks.
The results you're reporting here, I mean, it's absolutely fascinating stuff. It's measuring. I guess you're measuring the performance of the VMs themselves, but I mean, obviously we do similar kinds of experiments when we're actually measuring performance of applications. How does that interact with? I mean, is it a completely orthogonal thing, or is there an interaction here?
So is the question about whether or not the benchmark?
Well, would you expect these results to be specific to VMs per se, or is this something which generalizes to the performance of applications running on VMs?
I don't know. That's very hard. I don't know if...
The context for me is I've been doing, I do work on the Scala compiler, and we attempt to measure, deltas in compilation performance across, relatively small changes to the compiler infrastructure, and we do, the standard kind of benchmarks that you've described. And from what I'm seeing here, I'm assuming obviously all the results are bogus. Am I too hasty in making that generalization from what you're showing here about the VM to an application running on a VM?
I wouldn't like to speculate too much. So when you're talking about applications, you're probably talking about very different workloads to benchmarks, aren't you? So for example, these benchmarks are all completely CPU bound. That's quite rare for real applications, I would have thought. So maybe the behavior would be significantly different if you were to measure them using our tooling. I don't know. Don't know if I answered your question there or not.
Hi, just a quick clarification and then a more interesting question. I wanted to know, I didn't understand quite what you meant by checksums. You were checksumming the memory?
No. So for example, if we take say the Mandelbrot benchmark, this just prints out the Mandelbrot in ASCII, right?
Yeah.
So what I would do in that example was take the ASCII values and sum them all together, for example. And using that, you can then take an expected value and compare it against each run of the benchmark.
Okay. And then the more interesting question I had was, do you think you could repeat this experiment for a more larger, more practical applications? Because something like WordPress, for example, might have very, very different characteristics than something running a simple program many, many times. Do you think you could repeat the program, this kind of benchmark for a larger application?
So it's a very similar question to the last one.
Yeah.
So yeah, with something like, what did you say, WordPress, sorry?
Yeah, WordPress, just something a little bit larger, a little bit more realistic.
So you've got the network involved now.
Well,
right. This is what bothers me here.
I see what you're saying. Yeah, so basically no.
Well, I'm not saying no. I'm just saying I don't know.
Oh, I see. Okay. Well,
Thank you.
Thank you. That's good.
So I'm just curious, for the results that you showed where the slowdown was because of the GC that we saw, did you try, or is it worthwhile trying rerunning GC unintensive benchmarks, or probably reducing the effects of GC to see if that is actually the cause of the slowdown?
Well, is it not evident from the fact that the wall clock times are really coupled to the time spent in GC already?
Right. No. So I mean, for the other ones that you were not able to determine, I don't know if you did.
Oh, I see. So did we try and make them less GC intensive? We didn't try that. I mean, there's all manner of things we could try, actually, yeah. I've had all kinds of suggestions from the community. Any more questions?
Doesn't seem to be the case.
Okay.
Thank you once again.